तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 5 in mechanical measurements. Towards the end of the last lecture, we talked about linear regression and we took an example and quickly went through the example. So, what I am going to do in the present lecture is to continue from there. The slide shows the plan of action for this particular lecture. So, what I am planning to do is to use linear regression using Excel, which is a program available in the Microsoft Windows Office suite, and it is very useful for regression analysis, and by that we can avoid a lot of computations which has to be done by using the calculator if one wants to do that. Otherwise, the Windows environment in the Excel makes it very simple and easy. We will look at that as we go along. The next topic, of course, that will be through example 5, and the next topic will be multiple linear regression. I am going to give some hints as to how it is done, and I will usually use mostly the board to describe the procedure. Then I will take the topic of nonlinear regression, which is really what is required in many cases of interest to us. The nonlinear regression is more general, and in fact it encompasses whatever we have done earlier on linear regression, but a few new concepts are required, and one such concept which determines the goodness of the fit in the case of nonlinear fit is the index of correlation. So, we will look at the index of correlation and how it is obtained and what is the basis for it. That will again be worked out on the board, and I will follow it up with an example 6, which will be using the Excel again. So, before we proceed with the actual content of the lecture, let me just digress a little bit, and we will talk a little bit about Excel, which may be familiar to many students, but it is just nice to find out what are its capabilities, what it can do, and how it works. So, the Excel, which is a spreadsheet program, actually it is a program environment. It provides us an excellent tool for doing data analysis, and especially those who are going to do experiments either during their undergraduate program or later on will find it very useful. So, I will talk to some extent on Excel. Actually, when if I take up an example, automatically it will become clear as to what we are talking about. The point to note is that Excel is a tool for analysis, very useful, and as far as we are concerned, we are specifically interested in its use as shown in the slide. Can we go to the slide, please? Specifically, its use for tabulated data is important from the point of view of our present discussion. The advantage of the Excel spreadsheet program is that regression may be done automatically by using the options available in Excel. And what I am going to do is to show how Excel can be used for doing or performing a linear regression by taking a specific example, and I will indicate the steps involved in doing this analysis. I will also indicate how all the statistical parameters can be automatically obtained using Excel. The Windows Excel, as I was mentioning, is a very useful thing which provides us an easy way of doing the analysis, which is always to be done after performing an experiment. The analysis of data is also called post processing in the terminology of what we use, engineers use. So, what I am going to do is to first introduce the Excel as a program environment, indicate how it can be used, and then immediately follow it up with the example, which is going to be a linear regression example, and I will indicate how it is done in a very easy fashion. As you see from the slide, I have opened the Excel worksheet. This is called an Excel worksheet, and you will see that it is full of tables with each. This, for example, this is a cell. In this cell, I can either write a statement. For example, I will just say something here. I can just write something. I can erase it, and then or I can put a number, or I can put a formula. For putting a formula, I have to put equal to. That means that whatever is going to follow that is going to be a formula. For example, exponential of, let us say, 2. So, if I come out of that cell, the formula has been calculated. E to the power of 2 is 7.38, whatever is shown here. It has calculated, because whatever formula you give here, immediately it will calculate and give the value. The formula can also use, I will indicate here. For example, I will say equal to, that means that I am going to put a formula there. Let us say there is a cell which is identified A, column A, and row 12. This is the cell I am talking about. So, I am going to modify this. For example, I will say A12, there is a number in the cell number A12. I will multiply it by a factor of 2, just to indicate what we can do, star 2, and immediately it will give you the value 2.91, which is 1.458 multiplied by 2 is 2.91, etc. Actually, any cell here, I can refer to any other cell in this environment. We have any number of cells here. From any cell, I can take the number which is in that cell and perform some operation by putting equal to here and then invoking that cell number, invoke it, and then modify it by using a formula. So, the advantage of this environment now is very clear. I am able to enter either a text. Actually, I have entered a text here, as you can see. In this here, I have entered the text. In fact, text appears in the text box, which is not very clearly seen, but it is here. It appears there at the top here in this text bar. It is going to appear, and the text bar contains all the text I have entered here. The given data is expected to follow an exponential law, and that is what you see at the top here. And I can just come out of the cell, and it gives you what is in the cell in which you are currently positioned. So, in this cell, I have written simply x, and that is what you see in the formula bar or the text bar. This bar here, if you put an equal to, it becomes a text formula bar. If there is no equal sign preceding the whatever you are going to give, it becomes the text bar. Now, with this background, which is just enough to understand what is going on, let us take an example. The example is given or stated by giving the values of the time and the corresponding temperature, which is measured in a certain transient experiment. So, the time is given as t in seconds. Data is actually the difference in temperature between the whatever we are measuring, the temperature of whatever object we are measuring, compared to the ambient temperature. So, the difference is what I am plotting here, I am giving here, and the t, the seconds, is also identified as x in our normal terminology. Data t minus t ambient is identified as y. You will also notice that in these two cells as well as these two cells, I have simply given the data, given the text. The text here shows that this is the x value, this is the y value, and x corresponds to t in seconds. In bracket I have put seconds, y is data, t minus ambient, actually it is in degrees Celsius. I have not put it here because I have to increase the width. For example, I can make it wider and put the temperature indicator there if we want. That means that the cell can be resized by going up here and then dragging it and making it bigger or smaller as you want. Okay, now let us look at the data. The data is given as there are 6 data points 1, 2, 3, 4, 5, 6, and there are corresponding 6 values of temperatures. So 0.35, 60, 0.6, 50, 0.937, 40, 1.438, 30, 2.175, 20 and 3.25 times. This is the given data. The first thing which one will do is to make a plot of this, and for making a plot is very easy. You just block the cells. The first one corresponds to x values, the second corresponds to y values. These are pairs of values 0.35, 60, 0.6, 50 and so on. So, I have blocked these 2 sets of cells here, and if I go to the top you will see something here which is the chart wizard. So, if I press that, it will give me a way of making a plot. That is the great advantage of the Excel arrangement, Excel environment, because you can give the data in the form of tables, put it in those cells, and then just by using this chart wizard I will be able to make a plot directly. For example, I will make a scatter plot. In fact, the type of plot if you choose, you will see these are the types of plots, and what I will do is I will take a scatter plot. That means x and y are going to be plotted normally like what you would do, and I can either have only points or I can have points as well as joining lines, only joining lines and so on and so forth. So, different options are available. I can choose whichever option I want, then go to the next button, and then it will give you immediately you see that the plot has come here. And if you want, you can make it bigger, and you can either go back and make some changes if you want, or go to finish and complete the plotting process. What I will do is I will just cancel this because I have already plotted it. I will just show the plot, and the plot is the usual plot which we normally do. The plot has many options, and these options are: I can use text for the title, I can also indicate the axis titles here, axis titles, and also the axis numbers corresponding to the divisions, and then I can also this formula I will come to a little later. So, what I have here done is to compare the data with fit, but right now we do not know what the fit is. We are going to come to that later. Right now let us just look at the data. The data is the points here shown. There are 6 points which have come here, and the data is plotted just to indicate that it is not a straight line. It is very clear immediately that the plot is not a straight line. Therefore, I want to find out whether there is a different way of plotting which will probably give a straight line behavior. That means, if I take a look at this data which I took from the first worksheet, this data is not giving a straight line relationship between the x and y. So, in order to find out whether we can linearize this by, if you remember in the previous lecture, we have said that we can either have a log-log graph or a semi-log plot to find out whether the plot can be or the relationship can be linear in any one of them. So, what I will do is I will go and make a semi-log plot. For that, I can actually calculate the logarithm as is shown here. This will be logarithm of y or logarithm of t minus t ambient. This is the logarithm value. I have taken logarithm with respect to base e, therefore ln, and incidentally it is done by simply taking the logarithm with respect to base n, the e ln, in bracket I have given b5. If you go back here, you will see that this b5 is this cell. So, the formula here is logarithm of b5, which is in the cell number b5. This whatever number is here, it will take the logarithm and indicate here. There is another advantage. Suppose I remove this, I do not have this. For example, I deliberately deleted those things. Now, what I will do is, I will just drag this down and I will copy the, if you go to the edit menu, you will say fill down, the numbers have come back. That means, I do not have to write the formula every time. If the same formula is valid for more than one cell, all I have to do is to copy the formula down by filling in the formula, and immediately what happens, this will be logarithm of B5, next cell is logarithm B6, that means it has gone already to the next cell, and therefore, the copying the formula will also change the reference to the appropriate cell. In the previous case it was B5, it became B6 and so on. So, it will automatically run down, the formula will calculate as we go down by taking the suitable reference to the suitable cell. So, with this background, let us see what I have done in the next plot is I have plotted this one and this one. X is as such without any change, because I am making a semi logarithmic plot. Time axis is linear, the temperature axis is nonlinear and logarithmic. So, I am going to choose these two cells, these two columns and make the plot. That is what I have done here. It is semi log plot, which shows the logarithm of t minus t ambient as a function of t in seconds, and again we will come back to this later. So, we have the 6 data points here, and you see that it looks like there is a nice straight line relationship between the data points and the, in fact, I have shown that data the straight line, which looks like a reasonable representation of the data. So, in order to find out how to get the line, all I have to do is to go to the chart here, and there are several options here. There is a option called add trend line. This trend line, if I press that, it invokes several possibilities are there. The trend can be, this is linear, this is logarithmic, this is polynomial, this is power law type, exponential and moving average. So, let us not worry about all of them. Right now, I know that I am expecting a straight line relationship. So, I will click this. That means that the trend line I am going to get is going to be a straight line, and options are there. I can, for example, ask it to display the value of the correlation coefficient if I want. I can also ask it to display the equation on the chart. That means that the regression equation immediately will appear on the screen, and I can do that. So, these are all the choices I have. If I just say OK, it is already going to give the equation has come here. This is the equation. So, I will make it slightly bigger so that you can see it better. So, that is the equation. In fact, I already, that is the one I have brought here. So, what I will do is I will go back and undo what I did, so that the trend line option is not there. So, I will just clear this so that I do not have to worry about it. So, I have already done it, and what I see here is the formula logarithm of t minus t ambient is equal to minus 0.6065 t. So, this is the slope parameter plus 4.2837, this is the intercept parameter, and also it is giving me the R squared value 0.999 or 0.9989. That means that the trend line was obtained by simply by invoking the trend line from the chart option. So, if I add trend line, all I have to do is to just do that, and the calculation which we did in the last class of making the tables, adding all the x values, y values, the product of x y, the product x squared, and then finding out the covariance, variance, and then determining the parameters, the slope parameter and the intercept parameter, all that is done automatically by the program, and that is the great advantage of that. In fact, what I did was, after doing the semi-log plot and finding what was the appropriate relationship, I have gone back and I have plotted that in the form of an exponential plot, because if you remember, if the semi-log plot shows a straight line relationship between the two quantities, the relationship between the two variables is exponential in nature, and in fact the exponential relationship t minus t amp equal to 72.506. This comes from the constant and e to the power of minus 0.6065 t. This is the slope parameter. That is the slope parameter and the constant, and the two of them are going to come out like. In fact, I am going to show you how I do that. So let us look at the next here. So I get the intercept, which is 4.2837, is the logarithm of the intercept. Therefore, all I have to do is to take the exponential of this, that is nothing but the inverse of a logarithm, and I have that here, e to the power of E14. E14 is the number I have here. E14 is the number corresponding to E, and 14, this is the number. I have taken the exponential of that, and that is going to come in this particular. Actually, if I go and just click here and put a cursor there in the text bar or the equation bar, immediately indicates there is E14. It immediately shows with a blue border, in this case, the active cell from which I have taken the information. So this cell takes the value in this cell and immediately calculates whatever formula I have given, and the formula is the exponential of E14, and that is 72.4. And the correlation coefficient can be calculated by simply, either you can, actually you saw there that the correlation coefficient was given here already. It can also be calculated if one wants by doing the calculation like what we have indicated earlier. You calculate the mean values, slope, and so on and so forth, and you will be able to do that. So one can also do that. In fact, one can also do the following. I want to calculate what is the expected error in this fit, or the so called standard error in the fit. So for that, I compare the data with the fit. I have written here the numbers corresponding to the fit. How do I do that? Very simple. The fit is given by, this is the formula, 97 point minus 25. This is your 72.51 e to the power of minus A5 by 1.6487. This A5 is the t. 1.6487 is nothing but 1 over the value which was shown here. That slope parameter, I have taken the 1 over slope instead of in this form of slope. So this is the formula which I have given here, and I have calculated this formula down, and therefore these are the values of the fit values. And you can also see that the value of the given data is 60, this is 58.64, this is 50, 50.39, 40, 41.07. You see that they are close to each other. That means that the fit is certainly a good representation of the data. And in fact, in order to further find out whether it is good or bad, I am going to compare or obtain the standard error, and that is obtained by taking the square of the difference between t minus t, the data and the fit, and then adding all the squares. These are the errors, and then square of the error is given here, and then you find out the standard error. It is, I am taking 1.96 for 95% confidence level, square root of sum of, this is actually sum is a function available in the calculation, and I will just explain how it is done. E21 to E26, these are the values I am adding, and then dividing by 4, because I am going to divide by 4 because I have the number of degrees of freedom is n, the number of points 1, 2, 3, 4, 5, 6, minus the number of parameters 2, that is going to become 4. So this is the standard error expected in the calculation. I calculate it here. Now I can go to the plot and in fact show the standard error as an error bar. So, if I go to the data point format data series, I have an option for giving the error bar. The error bar, what I have done is that 1.87 I have written here in this option, so that it will give a bar like what is shown here, and that is what you see here. So, if you want, we can expand it slightly, so that we can look at that. In fact, I can do a little better. Where is the? I think that option is not here. Okay. So, anyway, you can see that by simply keying in the data onto the worksheet, and by manipulating the data very easily without much sweat, we are able to get the plot either in the form of a semi-log plot or in the form of usual plot, XY plot, or in fact I can do some other types of plots. What are the other types of plots? These plots are helpful in further finding out or further demonstrating how good the regression analysis has been, whether the data we collected is well represented by the formula we have decided to have, the regression line, in this case exponential or straight line, or any other formula which we might have obtained or chosen. So, for that I can make two more plots are possible. I can make an error plot, and which shows the error at each data point. This plot is very useful, because in this case you see that the error points are lying on both sides of the 0 line. This is the 0 error line. This line would have been the line on which all these data points would have been lying were there to be no error. Because there are errors at each data point, some points, these 3 points, these 2 points are on the positive side, these 4 points happen to be on the negative side. And you will also see that the closer these points are to this 0 line, the better is the fit. Indeed, we can see that they are laying very close to the lines, the maximum being about 1.5 and the minimum being about minus 1.1 or something like that. So, the error is between plus or minus 1.5, we can say that. And in fact, I can make one more plot which also gives me an indication of whether the fit is good or bad. What is this line? We plot the fit on the y axis, that is the value of the y obtained by the regression line on the y axis. On the x axis, I am going to use the data which is given. And if these two data, the data and the fit, if these two are going to agree completely or perfectly with each other, they will lie on a line. If I were to plot it on using the same scale on this axis as well as this axis, it would lie on a 45-degree line. And in fact, that 45-degree line, I have called it the parity line. Parity line means the line of parity between the data and the fit. So, you can see from here that the points are all lying very close to the parity line, and therefore, the fit is a good representation of the data which has been collected. So, this is very important. That means, just to summarize, I can make a plot like this to compare the data and the fit. I can also put the error bar on it. I can make a semi-log plot and I can do the same thing. I can make a parity plot and indicate how good the regression line is corresponding to the data. I can also make an error plot to find out what is the error between the line of the fit line and the data. So, there are several ways of plotting, each one supporting the other, or each one supporting the fact as to whether the fit is good or bad, and that is one possibility. Of course, the other possibility is to just find out whether the correlation coefficient is good or bad, and that is another thing which we can do. And in fact, I have calculated the correlation coefficient also. It is minus 0.9994, the negative sign because there is a decreasing trend as I have already indicated earlier, and this is another indication of how good the fit is. I have shown how the Excel program can be used to do a linear regression. Of course, the example I took was an exponential fit, but as we recall from the previous lectures, an exponential fit can be converted to a linear regression model by a simple semi-log plot or by taking the logarithm of the y values. So, to just recapitulate, we demonstrated the basic aspects of Excel as a computing environment, and hopefully the student will have learned enough so that he can continue from there. And also we took the linear regression as an example, the exponential fit, and we demonstrated how it is actually done using the Excel spreadsheet. And we also have indicated how different types of plots can be made to represent the data in a graphical form, and all these plots can be done by simply invoking the chart wizard, which was used actually, which was demonstrated to just show how the plotting is done. So, with this basic background, let us see what are the other kinds of regression which one may be interested in doing. I am going to talk about two things: the multiple linear regression, which also is a very useful regression model for many problems, many situations where multiple regression may be useful. The basic scheme I will indicate on the board, and let me just briefly say where you expect this kind of a model to come. So, I will just take a simple example. Let us take a sensor which measures the presence of water vapor, moisture. It is referred to as a hygrometer. And a hygrometer uses a sensor we will not go into the great details. We will just we assume that there is a sensor whose property, some property which of the material which is used in the sensor. For example, the electrical resistance. So, the electrical resistance of the sensor element varies with humidity. Hygrometer measures the humidity in the atmosphere, and the sensor which is used in the hygrometer has electrical property called electrical resistance, which varies with humidity. Unfortunately, it also varies with temperature. That is, if it were a function only of humidity, I would not have any problem, but it also varies with temperature. That means, if I say R is the resistance of the element, this is a function of humidity, which we can indicate as the relative humidity RH and temperature. So, the sensor responds to two quantities at the same time. It is a very typical example I am just trying to take. So, let us look at how we are going to do this. Of course, we do not know to start with what will be the type of functional relationship. Suppose we now generalize, instead of taking the hygrometer example, I can take a general example. Suppose I have a quantity z which is a function of x and y. In the example of the hygrometer, this will be the RH, this will be the temperature, and this will be the resistance. Of course, we need not have only two variables here, we can have more than two variables. However, if the relationship z equal to f of x y is linear, that means linear relationship means we have z equal to ax plus by plus c. There are three parameters a, b and c. This is the parameter, three parameters a, b and c, and the regression model will have to obtain three parameters by using the same principle which we have used earlier, the least square principle. So, let me just indicate the steps involved in this without taking any specific example. I will just indicate the steps involved. So, least squares principle means I am going to minimize some quantities S sigma over I equal to 1 to n, which are the number of data I have, Z I minus A x I plus B y I plus C whole square. So, I have to minimize the quantity which is shown here. So, again you will see that the simple procedure is very simple. I have to set dou S by dou A, dou S by dou B, dou S by dou C all equal to 0, and this will give three normal equations which have to be solved simultaneously. Actually, I will just give one normal equation. The student can work out how the other ones are going to look. So, suppose I take dou S by dou A. Let us see what is going to happen. So, we have dou S by dou A equal to sigma over I equal to 1 to n 2 into Z I minus A x I plus B y I plus C multiplied by minus x I. This is equal to, this is one normal equation. Similarly, I have to obtain the normal equation for dou S by dou B equal to 0, dou S by dou C equal to 0. So, three equations will come. Let us just look at the form of this equation. So, I have Z I multiplied by x I. I will send it to the, this is minus into minus, this becomes plus, this becomes minus. I will send it to the right hand side. This 2 is a factor which multiplies every term, therefore, I need not include it. So, you will see that I have A sigma x I squared plus C B sigma x I y I plus C sigma x I is equal to sigma Z I x I. So, you see that the first normal equation is written down by taking the derivative with respect to A and setting it equal to 0. And you will see that, of course, I have to put I equal to 1 to n in for all the summation, which I am just not doing it, because we assume that you can supply that information. So, it involves the square of the x values, then you see that it involves the product of x and y. It also involves this product of z and x. In fact, you can immediately see that when I take the derivative with respect to b, I will get here instead of x I squared, I will get x I y I. Here I will get y I squared, here I will get yi and here I will get zi yi. So, that is the second normal equation. When you take with respect to C, I will not get any product like this. So, it will be just a sigma xi plus p sigma yi plus c times n, the number of data, equal to sigma z. So, three normal equations are written down and solve to get A, B and C. Okay. So, it is a very straightforward and simple thing, and in fact the rest of the thing, like calculating the how good the fit is to be done by the following method. So, in the case of single variable, if you remember, we talked about the correlation coefficient. Here we have a problem, because there are too many variables which are there, two independent variables and one dependent variable. So, how do we define the correlation between these two? So, for that what I will do is, I will introduce the general concept of index of correlation. In fact, this is a general concept valid for any regression model. It need not be linear, it need not be multilinear like what we are talking about. It can be even nonlinear expression involving any complicated expression for any regression analysis. General concept valid for any analysis. So, let me just find out how to do this. So, let us just try to see how one can go about doing this. Suppose I make a plot, which of course can be done using Excel if you have actual data. I have so this is the y value. I am just doing it for single variable, but there is no need to restrict to single variable. This is x. Okay. So, the data was like this. So, let us take data points like this, and the relationship, the regression line or the regression curve is like this. This is your regression. I will say generally line also includes a straight line, it also includes a curved line. So, if I look at this, suppose I identify the mean value of the y. So, let us say mean value of the y is here. This is the mean y. So, if you look at this mean y, of course, we have known that it will pass through, this line will pass through that mean value. You see that with respect to the mean value of the y, these are the differences. If I draw a line from there to there, these are the differences. Okay. I have just taken a few points. If you have more points, you will see a much better description of what is happening. So, now I can look at the variation of y with respect to the mean and define sigma y squared as the variance of the y's. This concept is already familiar to us. The variance of the y's. Actually, how do we define? This will be given by sigma y minus y bar whole squared divided by n. This is what it is. Now, if you look at this graph, I have got a line which we call as the regression line here, and with respect to the regression line, there are errors. So, this is the error or the difference between the regression line and the data. Again we have a difference here and we have a difference here. So, I am just indicating the differences like this, and I am sorry, this is not the correct one. This is the difference I am talking about, and similarly here and here and so on. So, now I can also define a variance for the errors. So, I will just say, I will go to the next screen so that it is not cluttered. So, I can also define variance of the errors, or if you want to call them as differences with respect to the regression line. It is a very interesting thing to do. So, let us call that as S squared, or S squared is the variance of those things. This will be nothing but sigma of y I minus y fit whole squared divided by n. So, we see that we have defined a variance of the y's given by sigma y squared, which is given by this formula here. You can, this is equal to 1 to n, y minus y bar whole squared divided by n, or y I minus y bar whole squared divided by n, and y bar is of course sigma y by n, or sigma y I divided by n. So, just look at this quantity. This quantity is something which tells you how the data points are distributed with respect to the mean value of the y. So, now we will look at the other one, the variance of the errors. Variance of the errors is given by this quantity. This is nothing but the y I minus y fit whole squared divided by n. Y fit I, let us put it here, because that is at each point you must find out what is the value corresponding to that value of x, find out the y fit value, take the square of all these errors, divide by n, you get the variance of the errors. Now, I am going to compare the variance of the errors with respect to the variance of the y's. If the variance of the errors is small compared to the variance of the y's, that means if I go back to the previous page, I am comparing this quantity with the, that means that I am going to compare the variance with respect to the mean value of y bar and the variance with respect to the local mean value, because the fit represents the local mean. So, I am going to compare these two variances, and if the variance with respect to the local value is small compared to the variance with respect to the mean value of the y, then I can say that the whatever relationship I have obtained is good. So, how to mathematically put that? So, let us define what I call as the index of correlation. So, which is a mathematical expression. I will say this is the index of correlation. Instead of calling it the coefficient of correlation, I am going to call it an index of correlation. I can use the same symbol as I used earlier, either R or rho. From the context, it will be clear what we are talking about. It will be plus or minus square root of. I am going to again define such that if this index of correlation is very close to plus 1 or minus 1, I get perfect correlation. If it is very small, I will have to see, I will have to make sure that that represents a poor correlation. Therefore, if I do the following, if I take 1 minus s squared by sigma y squared, put it under the bracket and the square, take the square root, this will have that property. That means, perfect correlation when r is plus or minus 1 or close to plus or minus 1, and no correlation if r is close to 0. So, the index of correlation is a more general quantity, and in fact, it can be shown that the index of correlation and the correlation coefficient are only the same for a linear fit. So, I am not going to do it here, I am just stating without proof. It can be shown that the index of correlation and the correlation coefficient are identical if you have a linear regression model. So, with this background, let us look at the slide again and look at the multiple linear regression. Anyway, we have already shown how it is done. So, I am going to look at a general nonlinear regression. I will just be able to say a few words about the general nonlinear regression, and we will of course continue in the next lecture. So, this is more general and includes all the earlier cases we have considered, and they will be simply special cases. The method again is based on the least square principle, and the parameter estimation problem. If you remember, the least square principle gives me the sum of squares of differences between the data values which are given and the values obtained by the regression line or regression curve. That sum of squares must be made smallest. That means, I am looking at a function whose I must find the, or I must choose the parameters such that this sum becomes the smallest possible. Okay. That means, it is like an optimization problem. Optimization is finding either a maximum or a minimum for a function. Therefore, in this case, we can treat it as a optimization problem, and we use optimization methods to obtain the solution. Of course, in a few cases of nonlinear regression like polynomial, it is possible to do the regression again in terms of normal equations, solving them to get all the parameters. In the case of a general nonlinear regression model or problem, it is not possible to do that, and therefore, we have to do it using a mathematical technique, which basically is an optimization technique, and there are several techniques available. And what we will do is we will only indicate how it is done in a very general way and not take it up for any detailed discussion, because this will be outside the scope of the present set of lectures we are giving. So, I will talk about the polynomial fit, and the polynomial fit is also a nonlinear fit. The model will be, for example, I can just indicate a type of fit which is a polynomial fit. Let me just indicate briefly. For example, if I have one variable y which is related to x in the form of polynomial, I can have the following. I can say a naught plus a1 x plus a2 x squared plus, it is going to stop somewhere. So, you will see that, for example, linear, it stops here. It is a special case of a polynomial fit. It is actually a monomial. A quadratic will stop here. A cubic will stop with the cubic term, and so on. And you will notice that A linear has got 2 parameters. So, linear 2 parameters, I will just say 2p, p stands for parameter. Quadratic will be 3 parameters a0, a1, a2. So, this is 3p, and in general nth degree polynomial have an, a0. So, it is n plus 1 parameters. So, what I will do in the next lecture is to take simple example of a quadratic fit and show how it can be done using the Excel, and also try to understand how we calculate the goodness of the fit for that particular case. We will stop here and we will resume in the next lecture. Thank you.